Now we want to look at further velocity and acceleration. So in the 2-unit course we dealt with velocity and acceleration. So we've done questions in the 2-unit that dealt with that, but this time in that course, so everything was in play in terms of t. So all the equations you had were in terms of t. So you had your position displacement, or the position of the particle, was in terms of t. Then we derived that, and that got us the velocity. So dx dt was the velocity, but the function was with respect to t. And then the acceleration was the second derivative of that of the displacement with respect to t, or the derivative of the velocity with respect to t. Because we know that velocity is the rate of change of displacement, so it's how the position changes over time, and acceleration is the rate of change of the velocity over time. So that's where we get dv dt, so because we're looking at the rate of change. So that's what we had. So we had questions such as this. For a point moving along an x-axis, displacement is given by x in terms of that function t. So find when and where the first point first comes to rest. So we know when it comes at rest, the velocity is equal to 0. So we derived our function, and then we set it equal to 0. So there's our velocity equal to 0, and we get the t's values being 3 and 5 because we solved that quadratic. So where's it first at rest when t is equal to 3? So the position there is 34 units, because there's nothing along there. So 34 units to the right of the origin. So what's our acceleration then? So we get our derivative for our acceleration, and sub in 3. So our acceleration would be 6 times 3 minus 24, so or minus 6 units per second squared. So there's a force acting upon it, moving in the opposite direction of the way it is actually moving at that time. Well, it stopped at that time, so that's why it stopped, and it's going to move it back in the other direction. So that's how we started to do these questions. We could do integral calculus as well, so because we get a velocity function, and when t is equal to 0, x is 14. So we start to find out what the position is by taking the taking the integral of the function. We find our constant, and our constant we get there when t is equal to 0, x is equal to 14. So we have that. So we're able to work out that our constant is equal to 6. So there's our function, 5t plus 4 to the power of 3 on 2 plus 6. So it gives us our function for x. So the position of the particles given to us by x. So when t is equal to 9, we're able to start to put in 9 there, and gives us 349 units. And part B, from the time of moving a distance 19 units from the starting point, and corresponding sign for it to move in the same distance in the initial velocity. So for that, we get when x is equal to 33. So its starting point, when t was equal to 0, its starting point was 14. So another 19 units on from that would be 33. So the time for it to be 33 would end up being, we set up x being equal to 33 and solve for that. We end up with 5t equals 5, which means t is equal to 1 unit. So there's the time for it to get back to there. And so what we want to do in the extension 1 is still work with position, velocity, and acceleration. We still want to do all that. We still want to use our position statements, our velocity statements, and acceleration. But what we want to do this time makes it a little bit different, is have our velocity and acceleration in terms of the position. So instead of having the acceleration in terms of t, we want acceleration in terms of x. So what we get is this relationship, that the acceleration d squared x dt squared, so acceleration is going to be given to us by the derivative with respect to x of a half v squared, so half of the velocity squared. So that's the relationship we're going to start with, because all the functions we're going to get this time for our acceleration are going to be in terms of x. So instead of being in terms of t, your acceleration will be given in terms of x. So we need a different starting point, because that's not going to do it for us. Because that's giving us that's describing an expression in respect to t. So how do we prove this result? Well, we should be able to pick up at any point on this line and realize that any line here is equal to the acceleration, d squared x dt squared. So we're going to assume that velocity is dx dt because the acceleration is d squared x dt squared. So if that's the case, we can say that this expression can be given to us by the derivative of respect to t of the velocity. So ddx of dt. So that can be written then as the v. So dx dt is velocity, which we can then write as the derivative of velocity with respect to t. Now by the chain rule, we can say dv dx times dx dt. So we can write that statement. And dx dt, we know, is equal to v. From that, we have dv dx now times v, which I just rearranged and put v dv dx. Now, if I took the derivative of v, of a half v squared, if we took the derivative with respect to v there, that would give us v. So there's the half v squared. So dv of a half v squared times dv dx would give us, get rid of the dv's, and we get d dx of a half v squared. So there's our proof. All of those statements, any time, at any place, could be equal to the acceleration. So depending on what your acceleration is given to you, in what form, you could start to use any of those lines. Most of the time we're going to use the bottom one. But really, we could use any of those lines to say, well, my acceleration is given to me as this function, so my acceleration can be written in any one of these forms. So you might want to use something like that. Okay, or you might want to use something like that to describe the acceleration. Depends on what problem you're given. So have a look at that. Proof and be able to put any of those into place and know how we get from acceleration down to d dx and a half v squared. And in our next video, we're going to look at how we start to use that in problems.